Hello, how's it going? Hope you're doing well. Today we're going to talk about Newton's method. This is to solve equations, and we'll start out with the Taylor series expansion. You've probably seen this before in your math class, but here it is right there. So you can have a function, any continuous function, and that function can be approximated at a given x naught or a new x value given the previous or an x0 value from an expansion of the derivatives. So you can see there first derivative and the second derivative and the third derivative and so on. So this is just approximating the value next to x0 of the same function based on the derivatives. And with Newton's method, we just get rid of the second derivative and third derivatives and so on, and we just focus on this first derivative to give an approximation of, given an x value or a starting value, what the next value of x will be. And we want the new x value to be 0. That's the root definition. So when we set up our equations to solve, we talked about in fsolve that you set your equations in a way that everything's on the right-hand side or the left-hand side and the other side is 0. And we do the same thing here, and f of x is 0. And then you find the function value at your guess, for instance, and use the derivative at that guess value, where you can calculate the derivative. And then you find the new x value, which happens to be x right here. So you can rearrange this with f of x of 0, and you get this equation, and this is Newton's method right there. So let's say we have a function, x squared minus 5. So there's a plot of it, and you can see it's a parabola as expected, and here are the two roots, right close to minus 2.5. So we're just going to set a function that's called Newton, and we're going to plug in this equation, that function. So I've got, you have to know the derivative of the function, and of course the function itself, and you just loop through this over and over until you get closer and closer to 0, where that solution would be. So say we do this at a guess value way out here at 10 or minus 10, and we interpolate, or this is basically saying, if I draw a line with the slope, where does it run into 0? About 5.25 right there. So that's your new x value, and we plug that in again to Newton's function, and we estimate the slope and do the same thing, draw a straight line until it hits 0, and we get a new x. It's minus 3.1, and we keep doing that until it doesn't really change. 236, and is that equal to the square root of 5, which would be the solution? And you can see it's really close. And that's with only 10 or so iterations. So we're just going to plot those points as we move down. So you can see those right there. And here's a more complex example where you can differentiate it still everywhere. And this is the x to the 5th minus 5x to the 4th, so on right here. That's our function. We'll plot it, and here we got this little scenario here where if you get caught in this well, you'll actually never get to where the function equals 0, and you can't get out of it, because you can see if you're in here, you get the slope, you come down here, and then you might move over here, and then it might kick you out. But that's what's happening right here. I set up that derivative f prime and use my function value, the same thing as I did before, and do the same thing where I start at 5.5 and then get to 4.8 and so on. And then we're going to plot that, and you can see it kind of bounces around here in the well, but it never actually reaches where the function equals 0. So that's something to be aware of when you're using. The same thing happens with any derivative based method like fsolve or others, or gradient based. And so yeah, let's do a different equation now. This is as application. We had some homework with this, but with the Colebrook equation, and there it is right there. We've rearranged it so everything's on one side, and we want to set that to 0. So we're going to change the friction factor based on the Reynolds number and the diameter and the roughness, epsilon. And that's that Colebrook equation for the friction factor inside of a pipe. Use that to calculate friction losses. And we're just going to plot that function. And you can see there it is. It can be really helpful to plot the function you're trying to solve. Sometimes that's not possible if there's lots of variables. But there's that one. And there's different ways to get the derivative of this. So, because we need that for the Newton's method. And right here is one way. You can use the SciPy method to get the derivative. And you just basically say return the derivative of this with given parameters and arguments. Or you can use SymPy, the symbolic differentiation, and to not get everything confused with objects and so forth. As far as my f values and Reynolds numbers being defined as an object here and elsewhere not, I've labeled them differently, and there is my equation. So I can just type that in, which I did right there. And here is, I'll just use this one right here. You could use this one too, prime 2, but I'm just going to use this one. And my Newton method, Newt. So I got my friction factor, my new friction factor, and this is Newton's method. New friction factor given previous friction factor. Or rather, this will return the new friction factor given the previous one. So if I start at point 2 here, right there, it should linear extrapolate out here, and you can see, it goes negative. And what do you see in here in the derivative? Square root of a negative number. That's a problem. So here you get an error when you try to put this in, because as if you were to go over to negative and come up here, it would kick you back, but this equation results in an error. So there's ways around that, but one way is to change your guess value. We'll talk about other ways. So instead of 0.2, let's start at 0.1, closer to our answer. And you can see that eventually we get to 0.067, which according to our function looks about right in there. So instead of doing this line by line, let's do it with the loop instead of having to type it all out, like me typing this in the next step. So let's just do that. So I got I can make a values empty list, and then I'm appending the values of x. So I feed in a starting value and it appends it as the start, and then finds the new one with our Newton's method, and then sets the x value to x new, and so on and so forth. And here is the plot of the f of value. So you can see in this case, I did a trick. So instead of starting at 0.1, I modified Newton's method. So I multiplied the step size. This is the effective step size right here by a quarter value. And so now instead of going negative, it doesn't step as far, and it doesn't go negative. You can see it drops from 0.2 down to 0.13, and so on and so forth until it gets to a steady value around 12 iterations and levels out. So we can check if that value is at 0, so I can put my method in, and I'm just choosing the last value that it returned, which is way out here. And what is that value? It should be 0, and it is very close to that. So instead of doing that inside my Newton's method, I can also define a Newton next function, so it calculates the next value and returns it. And then instead of doing it for a certain amount of iterations, right here I've got 50 iterations. I just want to do it until the error goes down. So I'm got a little while loop right here. While the value is not changing, then I say sufficient. Don't need to do any more iterations. So you can see right there, if I do my Newton with 0.2, with also my modifier of a quarter of the step size from the derivative and Newton's method, and I can check that answer with fsolve, and there's my fsolve there using the arguments, and I get the same answer. So that's great. Well, perhaps not the same one, but very close, within 5 decimal places. Or looks like 4 significant figures. And so there's the Newton's method. I hope that's helpful, and we'll use that in your homework, and we'll talk about it in class. So here is so with this Newton's method here, we just solve for one variable. Well, what happens if you have 2 equations and 2 variables, or 2 unknowns? Well, there's a way to use Newton's method, and that's using a Jacobian matrix. So you need to understand or obtain the derivatives, in this case partial derivatives, with respect to the 2 variables. So let's say I have an equation like this. So x squared plus y minus 4. And here, instead of x's and y's, I've got an array or a list of x values. And these are my variables right here. So the first one is squared. The second one added to that and then subtracted 4. And my second equation is this. So if you were to write it typically, it'd be x minus y squared minus 1. But here I've got it as just a list of variables. And then I need my Jacobian matrix. So my Jacobian matrix is the derivative of the first equation with respect to the first variable. That happens to be 2x naught. And then on the same row, the derivative of the first equation with respect to the second variable, which happens to be 1. And then for the next row, the second equation, derivative of the first, which is 1, and then the derivative of the second, which is minus 2x1 right there. That's your Jacobian matrix. Then you can use Newton's equation in the same way, and but instead you have to solve, you have to invert the matrix. So this is just the derivative times some x equals the function value, and you're wanting that function value, this these equations here, to be 0. So you give it a guess for your x values, and then this is approximating the step size. Then you add it to the previous value, and then you can get a normalized vector or number from that array of guesses or step size. And if that's less than the tolerance of here we specify 1e to the minus 6, you can stop this and return the solution. So here's our guess, and then we spit in the Newton method is a function of these equations and the Jacobian right there, and my guess, and then there's the solution. So I hope that's helpful, and I know God lives and loves us.